Welcome to This Explainer. Today, we are diving straight into the nitty-gritty of ACI 318-19 footing design. We're going to completely bridge that gap between theoretical soil mechanics on one side and practical concrete structural design on the other. It's like putting the puzzle pieces of the earth and the building together.
Here's our roadmap for today. We'll cover 1. Basics and codal provisions, 2. Service versus factored loads, 3. Defining soil bearing pressures, 4. Shear capacity and flexure, 5. Essential foundation stability, and finally, 6. A detailed numerical footing example. Let's get right into it.
Section 1. Basics and codal provisions, framing the foundation.
We're starting our journey right at the source. Chapter 13 of the ACI 318-19 code. This chapter is absolutely crucial. It outlines exactly how foundation elements, whether they're isolated footings, combined footings, or massive mats, are explicitly responsible for safely transferring our building's entire load into the earth below. Think about it, right? Without this safe, engineered transfer, the structural integrity of literally everything built above ground is completely compromised.
Moving on to Section 2, Service versus Factored Loads, the two languages of design.
You know, to design a proper footing, you actually have to be fluent in two entirely different engineering languages. Geotechnical engineers speak the language of service loads, or allowable stress design, ASD. We use these raw, unfactored loads to determine exactly how big the footing's footprint has to be so we don't sink or cause soil failure. But once that area is locked in, structural engineers take the wheel using factored loads, LRFD. We apply load factors, like 1.2 for dead load and 1.6 for live load, just to figure out the internal concrete thickness and the steel reinforcement needed to stop the foundation itself from snapping in half.
All right, Section 3, defining soil-bearing pressures, gross, net, and factored.
Before we crunch any numbers, we absolutely must strictly define the three different soil pressures at play beneath our footing. First up is gross pressure. Imagine you are a tiny particle of soil sitting right under the base of the footing. Gross pressure is the total weight of absolutely everything pressing down on your shoulders. It's the applied building loads, the self-weight of the concrete footing itself, and the heavy soil overburden resting on top.
Next, we have net pressure. This is the big one for sizing our foundation area. By subtracting the weight of the footing and the dirt cover from the gross pressure, we isolate the pressure that is strictly due to the applied structural loads. We compare this net pressure against the soil's allowable bearing capacity. Effectively, we're just ignoring the dirt that was originally resting there anyway.
And finally, there's factored pressure. Returning to our two languages, once our footing area is locked in using the service loads, we completely switch gears into structural language. We take our factored axial loads and divide them by the area we just provided. We use this intense factored upward pressure to determine the internal shear and flexural stresses the concrete itself is going to have to endure.
Section 4, shear capacity and flexure, protecting the concrete from internal failure.
Let's see how we check those structural limits, especially for shear. We look at two critical sections here. For one-way shear, we check a distance D, which is the effective depth of the concrete away from the column face. We're essentially making sure the footing won't snap right across its entire width. Then, for two-way or punching shear, we evaluate closer in, at a perimeter distance of D/2 from the column face. This is to stop the column from literally punching right through the center of the footing, like a giant cookie cutter. The ACI code gives us specific formulas for both, ensuring our design strength safely exceeds these immense demands.
Now, to resist bending, we calculate the required area of steel based on the maximum moment at the column face. But hold on, ACI provision 24.4.3.2 steps in and strictly requires us to compare that calculated area against a minimum reinforcement ratio. For grade 60 steel, we have to provide at least 0.0018 of the gross concrete area. Basically, even if your math says you need barely any steel to hold the actual weight, you still have to provide at least this 0.0018 ratio just to control shrinkage and temperature cracking. It's a non-negotiable safeguard.
Section 5. Essential foundation stability, preventing shifting and tipping.
So our internal concrete is safe, but let's zoom out to the macroscopic picture. What happens when extreme lateral forces like hurricane winds or massive earthquakes violently push against the foundation? Well, if a foundation can't resist those lateral forces, all those beautiful internal structural calculations we just did become completely useless. The whole thing goes over.
To stop that from happening, we run sliding and overturning stability checks using our unfactored service-level loads. For sliding, we're relying on the friction between the rough concrete base and the soil beneath, plus any passive soil pressure pushing back. For overturning, the sheer dead weight of the structure and the massive footing itself provides a resisting moment to keep it anchored. For both of these critical checks, the code mandates a factor of safety strictly greater than 1.5. You want a big safety buffer here, for sure.
Section 6. Numerical Footing Example. Putting the theory into practice.
Okay, let's funnel all this theory into a real-world numerical proof for an 11.2-foot square footing. First, speaking our geotechnical language, we sum our service loads, the building weight, the footing, the soil cover, landing at a total axial load of 378.2 kips. That's heavy. With an applied lateral shear causing an overturning moment, we calculate an eccentricity of 1.26 feet. Now, because this is less than our Kern limit of 2 feet, which is just the footing length divided by 6, we know the entire bottom of the footing remains in full flat contact with the soil, no lifting. Finally, our maximum bearing pressure comes out to 3.28 kips per square foot, which is safely below our geotechnical limit of 4.0. Bam! The footing area is perfectly sized.
Next up, we switch to our structural language to verify the concrete thickness. Our factored upward pressure gives us a one-way shear demand of 176 kips at distance d. We calculate our capacity using the ACI formula, and we get 280 kips, so it passes easily. For the much more severe punching shear at distance d over 2, our demand jumps way up to 466 kips. But checking the minimum of the 3 ACI punching shear equations, our design capacity is 483 kips. Looking at these results, our structural capacity safely and brilliantly exceeds the immense factored demands for both shear types.
To wrap it up, we finalize our stability check. When we compare our resisting moment against our overturning moment, our actual factor of safety is a massive 4.77. I mean, we are blowing right past that required 1.5 limit, providing true peace of mind that this foundation is absolutely not tipping over anytime soon. So, we've checked all the boxes, but there's a really fascinating caveat found directly in the ACI code commentary. Does providing more strength always equal a safer structure? Ironically, no, it doesn't. The code explicitly warns that over-designing longitudinal reinforcement, like just throwing in too much flexural steel without proportionally increasing the concrete's shear capacity, can actually be incredibly dangerous. It could shift a potential failure from a safe, slow, bending failure that gives you warning signs into a sudden, catastrophic shear snap. It proves that in foundation design, it's not just about brute strength. Balance is absolutely everything. So here's a thought for you the next time you're sizing a foundation. Are you actually designing a safer structure, or are you just engineering a much more dangerous failure?